We are almost finished looking at the different representations to a mathematical function, but I do want to go on and explain one more part of that. And we have been talking a lot about domain and range for the whole last section we did. What 3.4 was completely covering domain and range only, and this is where it comes into play with our functions. So while we technically it felt like we just had one function up here, I did go on to tell you that for the pool problem, like when we just look at these numbers, technically we aren't, like, the real life scenario is not accounting for this continuous thing because it just doesn't apply to a lot of the situations that they would have in their family. So we can kind of think of that two different ways also when it comes to thinking about domain and range. So again, notice that the graph of the mathematical function, which we called it t is equal to 4s plus 4, but they just substituted in the y and the x, which is the same thing. They're saying that that is continuous because we said that we plotted the points and then we connected them. So we took these points and then we connected them with an arrow. So this arrow goes in both directions. So when we look at our graph up here, if we wanted to talk about our domain is going to be, how far does it go to the left and how far can it go to the right? And actually, because it has this arrow, it's going to go on forever in the positive and it's going to go on forever in the negative. So this domain it's not finite. It doesn't really end. So we would call it the set of all real numbers. And we would write that a certain way. So just to remember, domain goes left to right. So our domain of that is a set of all real numbers. And like I said, we use these brackets to represent the set of. And then also, when we look at our range, well, the range is going to continue to go up for infinity and down for negative infinity. So our range is also equal to the set of all real numbers. So when it comes to continuous, our domain and range look like this, all real numbers. But let's look at the difference when we compare it to Anthony's specific pool tiling problem. So Anthony's specific pool tiling problem is a discrete situation. So I'm going to come up here and I'm going to go back to where we had just the discrete. And I'm going to erase this orange line because we were just looking at the discrete situation. So in order to write his domain, we have to remember that Anthony only worked with whole tiles. He didn't work with half tiles or fractions of them. So when it came to his domain, it could only be like a tile size of, 1, 2, 3, pretty much where any number that's positive, so not equal to 0 and not less than 0. So we would write that as the domain is equal to, and it's going to be a set of numbers, but it's going to start with 1, 2, 3. It's going to keep going all the way up to an unknown number as long as n is a positive number. Positive whole number, and then ends the set. So pretty much any of those counting numbers, 1, 2, 3, 4, 5, 6, etc. And then for our range, this one's a little bit different because we said that for the range, that's going up and down. We weren't really counting by ones, we were counting by fours. We've got 4, 8, 12, 16, 20. So our range is going to look a little different. So I'm going to start with 8, 12, 16, and I'm going to keep going all the way up to an unknown. And actually, I'm going to use the algebraic rule or the mathematical function. So our function was 4 times that number plus 4. But again, with the stipulation where that n has to be a positive whole number. There we go. So really important to notice that for your discrete pool tiling problem, we just have a domain and a range that has dots for numbers. While if we have the continuous graph where it is with a line including in it, our domain and range is if there's no end to the line, it's going to be all real numbers in both directions. So going on to number 8 for the on your own, I'll actually get you started in a separate video for the on your own. I'll see you in the next